Tankfest, and the first of what I hope will be a series of interesting presentations here on the stage. I'm a great enthusiast when it comes to tanks, and one of the things I like about Tankfest is you can wander around the conservation hangar and explore what's in there, and there's all sorts of goodies in there. Some of it are vehicles which we haven't got room for in the main museum. Some are vehicles waiting restoration, some are prototypes, and then amongst those vehicles on display are experimental vehicles which were never intended to go into service, were never built as complete functional armoured vehicles in many cases. And it's interesting to think about why they were built. Were they just a figment of some mad engineer's imagination and he wanted to go out and try something out? Or did they have a real purpose? Did they actually go anywhere? Did the things that were tried out on those experimental vehicles, were they successful? So what I'm going to do is talk about some of the vehicles you'll find, experimental vehicles you'll find in the conservation hangar, and then for two of them, which I personally was involved in my career in the MOD, I'll go into a bit more detail so you can sort of understand a bit more of the thinking about the build and testing of these vehicles. Just so you know who I am, I'm William Suttle. I've worked for 45 years for the Ministry of Defence. Started my career at the Military Vehicles and Engineering Establishment at Chertsey, Chobham Common, home of Chobham Armour, and ended my career in the Defence and Science and Technology Laboratory last year. And during those years, I worked primarily on technology and research, but also on development and procurement. I have the privilege of being a trustee at this wonderful museum, and also found time to write a couple of books mainly focused on the development of post-war British armour. So I spent about 20 odd years working at Military Vehicles and Engineering Establishment at Chertsey, and that establishment was well known for experimental vehicles. So here's some of the examples which fortunately aren't available today. So we got Conres 75, that was the very first tank in the world to have a remote turret, an uncrewed turret, trying to get all the benefits of moving the crew out of the turret, so you've got a smaller silhouette high up. The Advanced Suspension Test Rig, that was built at a time when we were starting to look at active suspension, and we wanted something to compare active suspension with. So that was built to be the state of the art in terms of passive suspension systems, and you can see it there being put through its paces. FV4211, that was the very first tank in the world to be fitted with Chobham armour, so it's based on a Chieftain, and when that photograph was taken, that vehicle, even its very existence, was classified secret. And RPV1, that was one of a number of vehicles built to test high-dress suspension, which was very successfully developed and is now used on the Challenger tanks. That's some more unusual vehicles that came out of Chertsey. HMS Waterbug, an amphibious Land Rover with huge balloon tyres. Those tyres were actually manufactured at Cardington, the place up in Bedford where they built airships, so the people there built the tyres. And as you can see, it was quite successful in actually being able to float. The problem was when you were on dry land, turning those tyres put real stress on the steering system. Below that is a screw drive Land Rover, so between the wheels is like an Archimedes screw you could lower down on muddy terrain to help improve performance in very muddy conditions. Got there the gas turbine demonstrator based on the Conqueror. Some people say that was the world's first gas turbine powered armoured vehicle. Not quite true. The Germans put a jet engine in a Jag Tiger in the Second World War. However, that wasn't terribly successful. It had because they built it in a forest hidden away in Germany. It used to apparently used to set fire to trees. But interestingly, some people who worked on that project in Germany actually ended up working for the company who built the gas turbines, went into that demonstrator. And then below we got a Land Rover hovercraft. When the hovercrafts were invented, people suggested they were the next best things for mobility on the battlefield. Absolutely great on flat terrain. As soon as you try and go up a hill in a hovercraft, you can't steer it. So this was a sort of hybrid hovercraft when you needed it, Land Rover when you wanted to go up hills. So we ended up with something very complex and probably not a good combination of technologies. So that's some of the weird and wonderful vehicles from Chertsey that never made it to the museum. So now I'm going to talk about some that you will find next door in the conservation hangar. So Contentious 2. Contentious was an interesting project in the 1950s. It was known then that the Soviets had a lot more tanks than we had. So this was an exercise to say, if we reduce the cost of the tanks, if we reduce the number of crew in the tanks, for the same manpower and money, we can have a lot more tanks and try and redress that imbalance in numbers. Contentious 1 was a one-man tank. It had 4 120mm gun barrels on, each with a round up it, so basically you fired your 4 rounds and then you legged it somewhere safe to reload. But it had fairly thick front armour, but part of the logic was to say, because it's very small, it would be hard to hit. Anyway, the army didn't like that concept, so Contentious 2 had a 2-man crew, and it had just 2 gun barrels, each with like a revolving magazine at the back, each carrying 7 rounds. So that had 14 rounds. And the idea was it would cost a quarter of amount of a Conqueror tank. One of the ideas of reducing cost and making it lower silhouette was to change the elevation of the weapon by adjusting the suspension. So it's a bit like the Swedish S-tank where that was used. So a rig was built. What we were particularly interested in, or the engineers were particularly interested in, was how accurately you could aim the gun by adjusting the suspension. And so you can see on the picture some of the instrumentation, so they're measuring the accuracy of controlling the elevation. Unlike the Swedish S-tank, Contentious would have had some traverse, so you would aim the vehicle roughly in the direction of the threat, and the fine-tuning would be done by actually turning the barrels. Didn't actually go anywhere. However, some of the understanding and some of the technology in that suspension later went into hydrogas suspension. There's another vehicle you'll find next door, TV 15,000, and as you look at that you can see a lot of resemblance to the Scorpion, the CVRT Combat Reconnaissance Vehicle tracked range, and this was a sort of pre-prototype for the original Scorpion. The Army at the time, they wanted a new reconnaissance vehicle, so they had Saladin as a reconnaissance vehicle, and they wanted something to replace it which had better off-road mobility. There's a lot of focus there. There was a video playing talking about the nuclear weapons. They wanted vehicles that they could guarantee being able to drive across the nuclear battlefield where there were no roads, very rough terrain. So they wanted a tracked vehicle. The only problem was they wanted it to go as fast as the vehicle it was replacing, that wheeled Saladin. And so Scorpion, when it was coming into service, in terms of the speed it could do, was a huge change from what the Army were used to with sort of Centurion and Conquerors. So this vehicle was all about exploring the use of very high-speed tracked vehicles, and could you exploit the very low ground pressure and get good off-road performance. So it was built with aluminium armour to reduce weight, very high power-to-weight ratio, wide tracks for low ground pressure, and was successfully tested. A version of this vehicle with aluminium tracks could sustain 77 kilometres an hour, which is pretty quick for a tracked vehicle. And all those lessons fed into Scorpion, and some of the benefits of the mobility of Scorpion really showed themselves in conflict in the Falklands, where on very soft ground the vehicles could actually go to places where actually some of the soldiers struggled to walk. This is Rhino, a 6-wheeled demonstrator, quite a beast of a vehicle. Had a Meteor engine in, so it had the same engine as the Centurion tank, in a lot lighter platform. that suggested that there was interested in making a world version of Contentious based on this vehicle, but I've not seen any confirmation that that's true. And this demonstrator was all about demonstrating skid steer. So instead of having turning the wheels to steer, you actually brake the wheels on either side if you wanted to steer. And you think, why would you want to do that? Well, the diagrams show why. If you want a wheeled vehicle to have good off-road performance, you want the wheels to be as big as possible. So if you look at Boxer, the new 8x8 coming into British Army service, that has 8 huge wheels. It's got the biggest wheels of any 8x8 armoured vehicle. And so big wheels give you good off-road mobility. The problem is when you steer them, the wheels have to have space to turn into, which means this hull between the wheels has to be a lot narrower, so there's room for the wheels to turn. That means you've got less space low down, you have to push some of the required volume up, and that's why if you look at wheeled vehicles compared with tracked vehicles, they're a lot higher, they're a lot bulkier, they have a higher centre of gravity, so they're less stable. So having skid steer is a way of addressing that. You can push the hull out almost to the inside side of the wheels, so you can get a much more compact vehicle. The Army weren't convinced, so Rhino was built and demonstrated that skid steer is viable. This vehicle was actually driven all the way from military vehicles and engineering establishments in Chertsey in Surrey all the way up to the firing ranges in Scotland. I'm not quite sure what other road users thought of it, but it demonstrated that skid steer was a viable proposition. It's another demonstrator particularly aimed at the Army. FV4202, a sort of concept test bed for some of the ideas implemented on the Chieftain tank. And you can see included there is the turret concept. But one of the things of interest was having a reclining driver position. So in conventional tanks, the driver position is a bit like the upper picture. The driver is sat fairly upright. If he wants to go head up through the hatch, he opens the hatch, jacks up the seat. But clearly, the height of the hull needs to be high enough for him to sit like that and still have the hatch closed. So the suggestion was have a reclining driver position. You can lower the front of the hull of the vehicle, have a much more compact vehicle, less area to armour at the front. But clearly there was a question, if the driver is lying back like that looking for a periscope, can he still see out properly? Can he still control the vehicle? So FV4202 was built to test the concept, and it worked, and the Army tested it, they were happy with it, and so that design was fed into Chieftain and the later Challenger tanks. It also means that actually throughout an exercise, if there's some downtime, the driver has by far the most comfortable place to have a nap. So finally, 2 vehicles I'm going to go into a bit more detail about. So SID, the signal communication demonstrator, a big part of that was to demonstrate solutions to industry, and the advanced composite armoured vehicle platform, which was all about upscaling manufacturing techniques. So SID, signature installation demonstrator, this vehicle was the world's first practical low signature demonstrator. So everything a Chieftain does, SID will do. So same mobility, same lethality, same sighting system, same communications. So it was a fully functional main battle tank. I have to admit, the French actually built a low signature demonstrator before we did in the UK. Theirs was not a fully functional vehicle. It's based on an AMX-30. It didn't have a full set of sights, and you can actually elevate or depress the gun. So although it was a very good piece of work, it wasn't fully functional. We wanted, with SID, to show that you could design a low signature tank, that it was affordable, it was practical, it didn't push up the weight, didn't require exotic, difficult to make materials. We wanted to show that solutions were practical and robust, and if we were at the time working on how to reduce the thermal radar signatures of vehicles there's a pretty good chance potential adversaries were doing the same things. It also gave us a chance to understand what signature management would do, and hence how it might impact on future sensors. So really the outputs we were looking for, we wanted to demonstrate to the Army the benefits of signature management, so they would start to write into the requirements. We wanted to show industry how to meet those requirements. Both SID and ACAVP, they were built late 80s, early 90s. In 1982, much loved Margaret Thatcher, one of her less good decisions was to move the design of British armoured vehicles out of government and into industry. And so within the research community and the Ministry of Defence, we wanted to show new technologies to industry. We wanted industry to understand the benefits. We wanted industry to understand how they could implement these technologies into their products. So at the time, people like Vickers and Alvis and GKN were demonstrating to them. And as I say, we wanted to work with our colleagues working on next generation fuses and thermal images so they could understand the future threats. So what is SID? So it's Chieftain Base, first functional stealth tank. It was aimed mainly at radar and thermal signature reduction. Visual signature reduction, camouflage paints, things like the mobile camouflage system on the Megatron over in the tank part, they were well understood. So we focused on thermal radar as emerging threats. Thermal imagers were starting to come into service. Radar systems traditionally used to detect aircraft, being used more and more on the battlefield and for sensors. So that was aimed at, and the focus was on good design practice. Probably aware of stealth aircraft. Stealth aircraft are incredibly complex, very, very expensive, use lots of exotic materials. Why? Because they're up in the sky. If they're being observed by a sensor, there's nothing behind them, so they stand out. With a tank, we got the advantage, it's on the ground. If the user is making good use of terrain, it could be hidden amongst trees. So on the battlefield, tanks live in a good degree of clutter. So we don't have to make tanks invisible. All we have to do is make them sort of blend in with the background. And a lot of that you can do simply by good design practice, where you put things, how you shape the vehicle. But we also, we could use it to test materials where we needed materials. The original SID had a different thermal sleeve on the gun barrel, which was radar absorbing. We also had blow-off covers over the smoke discharges, which were radar absorbing. So we could test out some of those concepts. So it's now at the Tank Museum, and before you get your pen knives out to remove bits, we did remove all the classified materials before it was sent here. The build of SID was interesting. As I said, it was based on Chieftain. Chieftain makes a lot of use of large castings for the turret and the hull front. Castings are notoriously difficult to get the dimensions correct. So we couldn't simply take a drawing of a Chieftain and design the new parts, because every Chieftain is different. So what we did is we made a wooden mock-up first, so a full-size wooden pattern. It's easier to sort of shape wood to fit. And then we use that wooden pattern as the master for making parts of metal and other materials. You can see the picture top left. You can see 3 apertures along the side of the turret. They were for hatches, for extra storage around the turret. So on the left we got the sort of wooden mock-up. On the right you can see the vehicle being made. And in the bottom right picture you can see some of the things we're doing with the exhaust at the rear end to change the thermal signature. So if you look at SID next door, some of the things to look for. The engine cooling area of the exhaust come out at the rear and they're mixed together. Standard Chieftain, the engine cooling outlet louvers are on the top of the hull. So the top of the rear of the hull of Chieftain is very hot. So if you've got a surveillance aircraft, or these days a drone flying over, looking down, they would easily see the engine decks of Chieftain. So we put the exhaust out of the back, and the louvers are sort of angled, so we push the hot air and mix with the exhaust as far as possible directly out the back in a horizontal position, because the other thing you don't want to do is warm the ground behind you, or else they'll know something's there. Shaping to reduce radar signatures, not giving any secrets away by saying that if you want a low radar signature, you get rid of right-angled corners. So again, you'll see how we've tried to avoid right-angled corners, covered up things that did have right-angled corners, trying to get rid of some of the clutter. We provided extra undercover stowage, so tanks typically they have shovels and pickaxe handles and tow ropes stowed on the outside. All that needs to be covered up so it doesn't generate a radar return. So actually on SID we had 50% more undercover stowage on a standard chieftain, because we know that soldiers, they love to carry lots of extra stuff just in case they need it. We put covers on the hubs because the hub bearings get hot, and later on, after we built it, we put on track skirts, because track vehicles get very hot. So looking at SID from the front, without the track skirts, what you will see is the two hot tracks. So what did we do with SID? We did technical trials, so we measured the radar cross-section and the thermal signatures, say, yeah, have we actually got it lower than Chieftain? Then we did trials to quantify the benefits. So what does it mean in terms of reducing your detection range or probability of detection? So we could show to the army there was benefit in signature management. And we did robustness trials. So these pictures show trials of the skirts. We never particularly liked the design, not very elegant, so lots of jokes about Hawaiian skirts. But we did the trials, people down at ATDU, if something can be broken, the army are very innovative in finding ways of breaking it. But they trialled it and it survived. In terms of exploitation, because of the work on SID, the army started writing signature management requirements into specifications of future vehicles. To say, we had an industry along the likes of Vickers, GKN and AFVs, so they could understand how to use it. And say we worked with our colleagues working on future sensors, they could understand the future. So another vehicle you'll find, I think it's quite close to the entrance, the Advanced Composite Armoured Vehicle Platform, ACAVP, not quite as good a name as SID, but I didn't come up with a name unlike SID. ACAVP is the first AFV hull made completely of composite material. So the hull is basically made of GRP, glass reinforced plastic. The Americans, they built a composite vehicle before we did, but their composite vehicle had a metal lower hull and a composite GRP upper hull. ACAVP was all about practical production methods. So in essence, we were taking technology used to make canoes and saying, can you make a hull of a 30-ton tracked armoured vehicle using that same technology? How does it scale up? How do you deal with thicker sections? Development of engine mounts and suspension mounts was important. One of the reasons why the Americans had a metal lower hull, because if you've got a metal hull, you can drill holes, you can thread those holes, you can weld on mounting brackets. You can't do that with composites. So what ACAVP is, how do you make the inserts? How do you make inserts where you can mount the torsion bar ends, and where you can put the engine mounts? And we wanted to explore the weight and protection benefits. Again, very much aimed at industry, showing to industry how different materials could be used, and to demonstrate to the army that if industry came along with a composite vehicle, it was viable and would work. So some of the technical challenges, we had to work out what material to use, a balance of cost and performance. So ACAVP is made of high-grade S2 glass reinforced plastic. We had to work out how to make it. So it was made in two halves, lower hull, upper hull, bonded together. It was actually built by Vosper Thornycrofts, who make GRP minesweepers. But at the time, it was the thickest section GRP structure ever made. So there's lots of questions, if you know about materials. You know, GRP has the fibres, it has some sort of resin. We didn't know whether you could get the resin to set properly in the middle of a very thick section. We demonstrated schemes for mounting the various components. So ACAVP uses a Warrior engine and running gear. So it's got mountings for the torsion bars, mountings for the engine. And we put a turret race ring in, so it's got a box turret to sort of stress the hull. And in terms of protection, GRP on its own wouldn't have provided the levels of protection the Army wanted for this class of vehicle. So we wanted to explore its use as backing for applique armour, so whether that's high hardness steel or ceramic armours. A lot of work went into design. No one had ever tried this before, so in terms of designing the two sections of the hull, doing the stress analysis, making sure it was thick enough and man enough for the job, so we see some stress analysis work, computer aided design work, particularly looking at the stresses with the suspension mounts. Shows the final manufacturer, so I say it's made in two halves, so you've got the lower hull, a sort of boat-shaped hull, and then you've got the upper hull. See, the first time the two were brought together and they were bonded together. So in terms of outcomes, it was a successful program. ACAVP actually famously appeared on the Big Breakfast Show. One of the key engineers from the MOD who worked on it talking about it. And it demonstrated some savings in weight. I think a lot of claims were made in terms of weight savings, but at the end of the day, if you're talking about a 30-ton tank with applique armour, with running gear, with an engine, actually the hull is a relatively small proportion of the overall weight. But we're able to show that, like for like, you could save weight with composite hull. One of the big benefits with the composite hull comes from crew survivability, what we call behind armour effects, reduced behind armour effects. If you're in a vehicle and you're hit with a weapon that overmatches you, so the weapon actually penetrates the armour, what you will get is a lot of spool, what we call spool on the inside of the vehicle, so you will get a lot of hot metal fragments which will come out in a very wide cone inside the vehicle. Obviously very lethal to the crew, very damaging to the equipment. With a composite hull, it gives two benefits. One, because it's composite, fragments of composite aren't as lethal as fragments of metal. They're not so hot, they're not so hard, they won't do so much damage. So there's that benefit. The other benefit is if you get overmatched and you've got a composite hull, we get what we call a spool liner effect. So the actual cone of damage, the cone of fragments coming out, is a lot smaller. So the area immediately around where the vehicle's hit will be still damaged, but a lot of the vehicle won't be affected. And if you've got sort of the crew distributed, perhaps one of the crew members may get seriously injured, but the others will be a lot less at risk. And the technology on ACAVP was used on the Fox Sound. So over in the park over there is a Fox Sound. The crew compartment on Fox Sound is made of GRP. The same people who worked on ACAVP helped with the design of Fox Sound. So that's a case where the technology has been taken forward, where the weight and survivability benefits of GRP were exploited. So that's a sort of run through of some of the experimental vehicles. So I hope if you go into the conservation hangar next door and you see some of these vehicles, you have a bit more understanding as to why they were built, what they achieved, and some of the challenges they tried to address. As you can sort of wander around, see and try and spot where we've changed the design and why we changed the design. So that concludes my presentation. I'm more than happy to take any questions. So I think there's someone with a roving mic, if there's any questions.
Do raise your hands if you have any questions.
In terms of the sort of like heat signature, would the composite material dampen that, or what's the effect in terms of giving off?
Yeah, the composites can be worse. The challenge with composites is solar heating. So you all know how hot cars get on a hot day. If you've got a nice metal tank, if the sun shines on it, there's a big bulk of metal to heat up. With the composite, because it's a low conductivity, if the sun shines on it, the surface will get very hot very quickly. The sort of counter to that is because it's an insulator, if you've got a hot engine compartment, the engine heat can't get out. So it's sort of pros and cons. It's an area where you can actually use special paints on the outside to reduce the thermal signature. But it's an area where you have to look at it has benefits in some respects, disadvantages in other respects.
Has the composite development influenced the move to Boxer away from Warrior?
Not the composite part. The sort of move to Boxer is sort of quite complex. Boxer has very different mobility than Warrior, so Boxer is wheeled, so it's got very big wheels, so for its class it has got quite good off-road capability, but not as good as Warrior. Part of the thinking, particularly more recently, is the Army wants good operational mobility. So a problem with a tracked vehicle is actually getting it to where it's needed. So Boxer can drive long distances because it's wheeled, you don't get the vibration in a tracked vehicle. So I think it's more to do with that operational mobility benefits than the composites.
Hello. With the area where the lower and upper hull are bonded together, how did you avoid making that into a point of weakness?
Again, a lot of research went into the bonding process and actually making sure it was robust. So then that comes back to, why did we build it? No one had tried this before. Obviously looked at a range of different bonding techniques and adhesives to make sure we came up with something that was robust and wouldn't sort of delaminate when hit. Before ACAVP was built, there were a lot of sort of test rigs built, a lot of sort of small scale, so we come up with some small scale test pieces, bonded them together, put them on a test rig, make sure they were robust. We even did some sort of shock trials to make sure they would come apart in the event of a weapon hit.
Hi. Isn't it a lot more difficult to repair a composite tank if it has some kind of failure outside in the field compared to a metallic?
It certainly can be, but again, we did do a bit of work on repair. You can sort of patch it up, but generally, it's the area of damage. So famously, the Israelis with Centurion, there's stories of Centurions being hit in the Golan Heights, and they basically put a wooden plug in the hole and carried on. With a composite vehicle, you can have repair kits, just as you have GRP based repair kits for car bodywork. So you can do it. Interestingly, if someone drives into a composite vehicle because it's thicker and more rigid, actually it won't bend like sort of thinner bits of a metal vehicle. So again, there's sort of pros and cons.
Hello. Which innovation over your career are you most proud of?
Certainly, so I worked on both SID and ACAVP. I think SID, because it sort of did make a difference. I can't really talk a lot of detail about how it found its way into service, but one thing, if you go and look at Megatron and look at the exhaust ducts which take the exhaust to rear, some of the technology for that came from the work we did on SID and related activities, so that's good. Probably more recently, before I retired, I was actually doing some work on mobility and coming up with some very interesting solutions, so that was good. But I think in terms of SID, we were world leaders at the time. And yeah, it's always good. Yeah, if you're working on, if you're doing research, what you really want to see is your research find its way into things on the battlefield, and certainly we achieved that with Sid.
I have two questions. The first one is radar for ground target detection effective in current warfare? And the second is why is cast armor generally weaker than welded armor?
So on the first one, let's say, with radar on the battlefield, it's very much to do with the clutter. One of the challenges with radar is if you're moving, you get a sort of Doppler effect, so that helps extract you from the clutter. But even with Doppler, yeah, a lot of surveillance radars, what they're doing is searching a very wide area. And so they're just looking for hotspots. So if you can get rid of the hotspots, yeah, you won't be totally invisible. But if you've got a guy with a surveillance radar and he's sort of listening to some high-pitched noise when it thinks it's detected something, yeah, if you've got a low signature, you'll be less, you won't stick out. So it's all about reducing Q features, reducing saw thumb. As I say, Sid is by no means invisible. People in my career have come to me and said, yeah, we've invented the Harry Potter invisibility cloak. The Harry Potter invisibility cloak does not work, only at sort of one range and one angle of view. But so it's all about hiding in the content. On cast armor is very good. I say the problem with it is if you're got a 15, 20 ton casting that you put into a mould, pour hot metal into a mould and then you cool it down, it's very difficult to control the dimensions. So that's the trouble. And that doesn't necessarily mean it's weaker, it just means dimensionally it's more difficult. And it means on Chieftain, certainly when we, the later marks of Chieftain had the steel brew armour and the Togs thermal imager fitted, that was quite involved. You couldn't simply come up with a set of mountings. You had to sort of almost tailor-make each fit for each chieftain because they're all, slightly different in terms of dimensions.
Thank you.
Any other questions? In which case, a round of applause for William. Thank you very much.